We present a system that can learn to realistically change the appearance of an input image to another one corresponding to a different style presented in the dataset. In this example, the model has been trained on the dataset of landscape photos taken at different times of the day. Notably, the model learns from still images without any daytime labels. We show that by learning only from the still images without any temporal information, our network is capable of producing smooth daytime transitions. To create a plausible daytime landscape image, the model should preserve details from the original image. To satisfy this requirement, we enhance the architecture inspired by few-shot unsupervised image-to-image translation model with dense skip connections between the downsampling and upsampling parts of the generator. To preserve a style, we introduce an additional convolutional block with adaptive instance normalization and apply it to the skip connections. Content is saved by using off-the-shelf prediction of segmentation map. The overall architecture has the following structure. The content encoder maps the initial image to a 3D tensor of content using several convolutional downsampling layers and residual blocks. The style encoder is a fully convolutional network that ends with global pooling and a compressing one-by-one convolutional layer. The generator processes content tensor with several residual blocks and adaptive instance normalization models inside and then upsamples it. Autoencoding branch. We decompose the original image into the content and style latent codes and reconstruct them afterwards. Both style and content encoders take only the image from the decoder output and ignore the predicted segmentation mask. L1 distance estimates the discrepancy between the original and reconstructed image. Noise branch. The original image is translated to the random style sampled from the prior distribution. After that, the obtained image is fed to the autoencoder. Adversarial losses enforce the plausibility of the generated image and consistency with sampled random style. Latent reconstruction losses are applied to the extracted content and style, while image reconstruction loss compare generated image with his reconstruction. The segmentation loss checks whether the obtained mask mimics the externally provided segmentation of the original image. Swapping branch. This branch considers two real images that exchange the extracted styles between each other. We apply the swapping twice to introduce the cross-cycle consistency constraint. The cross-cycle consistency loss function intends to reconstruct the original image after being transferred twice. Other losses are similar to the noise branch, excluding the style reconstruction criterion. To avoid collapsing style encoder to a constant output, we apply a more robust objective than common L2 distance. During training, we also use two discriminators, general and conditional. In order to further improve the generated images, we use a separate enhancement network. The architecture is inspired by ESRGAN and Pix2Pix HD. The network takes 4 to 16 images, which are basically downsampled crops from the original image with a stride of a couple of pixels. Stride equals 1 for the 16 image case, translated with a high-resolution daytime translation model individually as an input and produces a single 4-time upscaled image as an output. We train it with perceptual, adversarial, and feature matching losses. We consider 3 upsampling schemes: guided image filtering, direct application of the trained fully convolutional translation network to the high-resolution input, and our enhancement approach. All these methods have issues, and overall the proposed method overcomes some limitations of its competitors. We demonstrate the style interpolation by linearly interpolating between two style codes extracted from different images, moving from cloudy to clear sky and from dusk to sunset. These images showcase the style swapping between two images. The trained model copes with exchanging the styles while preserving the content. The proposed approach may be used to generate static time lapses from a single image, using either an external video as a guidance or a predefined continuous trajectory from the latent style space. Note that modeling object motions, clouds for instance, is out of the scope for the present paper. Besides, we have no video consistency losses during the training process. High-resolution daytime translation model trained on a dataset of paintings is capable of artistic style transfer as well. Original images are shown on the main diagonal. Thank you for your attention.